Thanks. I feel like I should respond to that introduction by actually telling an embarrassing story about Danny. Yeah, I'm going to talk today about this project on the emergence of conventions. This is with a co-author of mine, Andrea Baron-Kelly. And this work really, I guess we have a lot of different disciplines represented here. This work straddles several disciplines. It really is a project that interacts with sociology directly and computer science and physics. And in fact, my collaborator on this, Andrea Baron-Kelly, is a physicist at City University London. And what we were really interested in was how, and in some sense whether, distributed interactions among individuals can collectively produce coherent consensus around a social convention or a norm. And I want to really just take a second to think about how we've talked about this problem typically, and even how I've talked about it in my own research up till now. The way we typically think about social norms or social conventions is a kind of a diffusion problem, right? This is the way my work, if people are familiar with it in the last 7 years, has really thought about how the structure of a social network affects the process of social diffusion, the spread of behaviors. And we think about a bunch of individuals connected in some sort of complex topology, and then there's a sort of seed person, there's an exogenous influence that introduces a behavior into a population. And then through some sort of process of social influence, it sort of spreads from person to person, and the contagion diffuses throughout the population. And this is the model that a lot of us use, and that I've been using for a few years as well, to kind of think about the spread of social norms. So I'm going to make a really clear distinction between this kind of thinking and the sort of project I'm going to engage in today. And so the goal of the project today is to say, well, look, this assumes there's basically a binary state. Either you haven't adopted a behavior, or you're exposed to it and you're convinced to adopt it and you do adopt it. And that's it. That's sort of the universe of possibilities. And what I want to ask about is, well, what about how when people interact with one another in kind of a real-time way, where as I learn about your behavior, I adjust and respond. I sort of change my expectations about what I should be doing. And as I do that, you're paying attention, you're learning, and you're also adjusting your expectations. And through these interactions, we actually engage in sort of a social evolution where we produce new behaviors. That sort of spontaneous ability to respond in real time to one another and produce new behaviors makes it less of a diffusion problem and more of an evolutionary problem about how these dynamics really evolve. And I want to really sort of unpack this question of social norms and social conventions this way. And because a large part of the literature on this really addresses this question of how we form these expectations, how we form beliefs about other people's behavior, and particularly in contexts like language, what kinds of words to use, what kinds of language to use in different social contexts, what kinds of politeness norms to exhibit, how to engage one another in different kinds of professional, personal, and private settings. And in these situations, what matters to us most is doing something the other person feels comfortable with, but also in understanding and interpreting the other person's behavior correctly. And through these kinds of back and forth dynamics, we coordinate and develop a set of behaviors that allow us to predict and form good expectations for one another, both emotionally, behaviorally, and in terms of our beliefs and expectations about the states of other people's minds. One of the most amazing thing about these kinds of norms is that once this process takes hold of a population, once a norm sort of becomes concrete and stable over a large population, it can appear as though it could not have been any other way. And what I mean by that is, if we have a norm of fairness, and we all sort of understand that norm, we were born into that norm, everyone else exhibits that same norm, we tend to believe that there's some sort of moral grounding for that norm. It's right in some sort of principled way. Or more sociologically or more theoretically, we can maybe argue that the norm is functional. It's performing some function for the society. It's doing some work that another norm wouldn't do. But we see lots and lots of cases where norms are relatively arbitrary, one norm or another norm. We go across different societies, and we see entrenched beliefs about politeness or entrenched beliefs about fairness look very different in different societies. Nevertheless, within a given group, there's this sort of commitment to the rightness of that particular norm. Furthermore, some work I did a few years ago on the Emperor's Dilemma pointed out that some norms not only are arbitrary, but are actually detrimental. There are some situations where people not only comply with the behavior, but actually enforce a behavior that they don't want individually. Not only do they not want it individually, it's welfare reducing at the individual level and welfare reducing at the collective level. So it really raises this question of how large populations can coherently all agree on a consensus behavior that no one wants and is reducing the value of the behavior for the entire population. Is there a question here?
So do you have like a measure of fitness, or do you look upon
So you just walked in, right? So I'm just getting going. This is only the second slide, right? And so this really raises the question of how we're able to understand the emergence of sort of large-scale coordination of our population when none of these behaviors can be justified in the abstract. And we have lots of theories. Over the last several hundred years, there's sort of three big ideas that have come out of the literature. The first one is that there's some sort of exogenous authority. Right? There's some sort of, either in a governmental context, there's some sort of ruler who essentially assigns sanctions or rewards to certain kinds of behaviors. Everyone responds to those sanctions and rewards, and thereby coordinates the population. This isn't only in governmental context, also in organizational context. We see this every day. Organizations put out formal and informal statements about dress code, about professional conduct, about gender relations, and people are expected to coordinate with that, and in so doing, they coordinate with each other. And thereby, these sort of top-down strategies are very, very successful at organizing large-scale behavior coordination. But one of the ways this has been pushed back, and this is for several hundred years, this has been talked about, but this has been pushed back on by the literature because people say, well, look, we also have large-scale coordination in situations where there isn't a centralized authority. Right? So how is that possible? There's got to be some other explanation for what can drive this. And this is where Harsanyi and Zelton's work, they won the Nobel Prize for this on what's called equilibrium selection, but it's basically you got a bunch of arbitrary possible outcome states. How do we choose between them? And they have some really good answers. They say, well, if you don't have an authority or a centralized figure or sort of explicit incentive for a certain behavior, the behaviors themselves, intrinsic to the behavior, can be different from one another. And that difference is detectable by every single person. So what they essentially come up with were two concepts. One is payoff dominance. It just means that if you've got two options, A and B, A is clearly better than B, and everyone perceives that fact. And so everyone individually gravitates towards A. This becomes self-reinforcing, and the whole population does A. The more subtle result, and the more interesting one in some sense, is risk dominance, which is that, well, there may be payoff differences between A and B, but A is a little safer than B. So given noise, given uncertainty, I may gravitate towards A for that reason. You, being equally rational, gravitate towards A for the similar reason, and then we collectively all gravitate towards A. A becomes a self-reinforcing equilibrium. This is a very clever solution. Like I said, they won the Nobel Prize for it. But there's a sort of a non-obvious but thick institutional assumption, which is that there's only two options in the population, or some fixed number of options in the population, and we all know what those options are ahead of time, and those options have payoffs assigned to them, and we all know what those payoffs are ahead of time. Right? So we're assuming a world in which basically the state of all possibilities and the reward for all possibilities is known a priori. And coming into that world, then we can all coordinate. But it doesn't really engage the possibility of a world where we can respond to each other creatively and produce new options. And of course, when that's happening, when new opportunities are springing up all the time and we're responding to each other, we don't really know what the behavioral reward is going to be for any given option. We just know that we want to coordinate. So the most contemporary way of sort of handling this, and those sort of the large literature that's growing up around feedback effects and cumulative advantage effects in popularity, is really about this idea of some sort of informational feedback, where essentially there's a centralized aggregation source that goes around and samples everyone in the population and says, what are you doing, what are you doing, what are you doing, what are you doing, polls everyone, and then basically collates that and reports it back in some sort of unified way that everyone can understand, and says this is what the rest of the world is doing. Now everyone's paying attention to the centralized source, and by seeing that, they then coordinate their behavior with what the majority of people are doing. This becomes self-reinforcing, and you get coordination. Again, this is a more subtle and sophisticated way of thinking about large-scale coordination and doesn't require the overhead of the first two. But again, there's really thick institutional assumptions built in. One is that we've got some kind of centralized system for polling everyone in the population. The second is that when we can aggregate coherently, speaking of norms, we can aggregate coherently everyone's state, and then we can report it back in a way that everyone understands, that's intelligible. And by the way, everyone just happens to be paying attention to simultaneously, right? And we do have these, right? We have bestseller lists, and we have other kinds of ways of sort of reporting in a polling for presidential candidates, right? We're all kind of paying attention to this. But for the kinds of social norms that we're thinking about, these sort of distributed social phenomena that emerge endogenously, linguistic conventions, gender conventions, politeness conventions, fairness conventions. These are things that aren't often reported in a systematic real-time way, which again, and this is really gets to the kind of heart of the theoretical problem, it sort of begs the question to say social institutions are the ground of the creation of social institutions, right? If we can't get coordinated conventions and norms off the ground without assuming that some institution that already exists to do that, then we don't really understand where these things come from in the first place. So this is where the social evolutionary approach comes from. It's basically a response to this entire literature. And it's an argument that suggests that people interacting locally, just with one another, trying to coordinate an everyday behavior, can, even though they have no idea what the world is doing, even though they have no rewards based on what the world is doing, can nevertheless, as an entire population, just wind up through the dynamics of interaction, coordinating with one another. Now, the problem I'm going to focus on today is how we would ever study this kind of thing empirically. It's an incredibly hard problem for the obvious reason that any single norm that we'd want to pick to study that would be interesting has already gone through a significant evolutionary process. It's hard to kind of get this thing from scratch to see how it evolves off the ground. So when we think about linguistic conventions, norms about monetary exchange, standards of fairness, gender conventions, also coordination and collective action, there's long histories that people are engaged in. An example I like to think about in this context, something like spam, right? The words, if I say I have spam, you're probably going to think I'm talking about junk email. But it's a weird linguistic convention, which is to say, 20 years ago, if someone said that, that would be just really odd. And so the fact that we all use those terms, we use that term to refer to something as arbitrary as email, comes from somewhere. There's some process that gives rise to it. And I was talking to someone who said, yeah, we all say spam because Gmail says spam in the spam folder, right? That's what they call it, and that's why we call it that. The irony of this is that the reason that Gmail uses the term spam is because everyone was using the term spam, right? People were using it. It emerged through sort of a natural linguistic convention, and then it was further institutionalized by an organization who was coming along like later in the stream. What we do even later down in the stream is then take our most intuitive theory, which is an organization tells us what to do and we all do it, and we attribute causally the origin of the term to that organization, right? And so this makes it really hard to get at any of these phenomena once they're subsequently entrenched and codified. So this really motivates the approach I'm going to talk about today. So I'm going to sort of introduce a method, which is the kind of thing I've been working on over the last 7 or 8 years, of what I think of as sociological experiments. And the idea is taking entire societies, watching them evolve, and then sort of deducing what the necessary factors were for this evolution, and then building another entire society and watching it evolve. For anyone who works on models, this is exactly what we do. We build a world, we structure a network, and we watch the thing evolve. When we go to data, right, the problem is, well, how would we ever get those kinds of data? I mean, the model is a pure and beautiful world. The data are incredibly messy, and just getting data that look even remotely like the kinds of models we have is hard. So if you've got 100,000 people connected in a network, that would be exciting. And if you got 100,000 people connected in a network where their behavior is changing in real time, that would be phenomenal. You'd say, I've got a great data set. And I'd say, well, how many data points do you have if you're going to study the evolution of behavior in that population? Under the assumption that people are connected to one another, under the assumption that people are interacting, if that's the theoretical basis of your project, you don't have 100,000 data points. You've got one data point, right? Because by definition, if people are connected to one another interacting, those data points are not IID. They're not identically independently distributed, right? They're all interdependent, and that's the point. That's the theory, is that they are interdependent, and that generates a collective phenomenon, which means your dependent variable is the collective phenomenon, right? It's just the observation of that single population. So if you want to compare that process in a repeated way and evaluate some structural variable that affects it in some systematic way, you need to be able to reproduce the population again and again and again. And I think of this method as something that's been around in sociology for a long time. I think about this intuition even going back to Durkheim, where in Suicide he tried to sort of compare different societies, isolate their differences, and suggest that we could sort of say each of these cases stand as single observations that then can be compared to one another and produce a sort of coherent collective view of how societies evolve under different structural conditions. And what I'm going to suggest is we can do that experimentally now in a very systematic way. And our argument is that the collective convergence of a population doesn't depend on the kinds of options that are available. It's not like there's a particularly good option in this population, so they all converge. No good options showed up here, so they didn't. The argument is, independent of the options that are available, just by structuring the population in one way, you're going to get convergence. You're going to be able to generate large-scale social coordination. And in another population where there's a lot of great options, you're not going to be able to generate convergence if the structure is different. So that's going to be the theory. And the structure here can mean many different things, but I'm going to interpret it specifically as a network theory. So I'm going to say if I change the connectivity of the population, just that one fact, which has nothing to do with the options that are in circulation, can causally affect, and that's going to be a strong causal claim, which I'm going to hope to back up experimentally, but can causally affect whether or not a population will produce a coherent social convention or social norm. So I'm going to give a little bit of theoretical background on this, my approach, the way that I'm thinking about this from a modeling perspective. I'm going to talk about the experimental design briefly and then get right into the findings, which I think are fairly interesting. So the theoretical background for this, evolutionary models more generally, is that we typically assume cognitively very, very simplistic agents. So agents that are kind of interacting in a network. People have seen these diagrams before, but there's an individual, and these links represents the people that they interact with. So this person has 2 neighbors on the left and 2 neighbors on the right. And at every interaction, they sample a person from their local neighborhood, and they try to coordinate with that person. In this network, people, again, have 4 neighbors, but those neighbors are randomly distributed. As you guys all know, what that does is essentially reduce the degree of separation between people and make it much faster for information to spread across the network. Finally, we have this this is the case that most economists have used and early physics models used, which is the homogeneous mixing case, which is basically selection with replacement. So I pick one person from the population at random, I interact with that person, I put them back into the pool and repeat. Right? And so this is the case where basically this could be called both no network structure or a fully connected network structure. Right? But basically at each iteration you have full access to the entire population. The thing to remember is that in each of these networks, including this one, people can't see the state of the world at large. They just see the state of the person that they happen to be interacting with. And our goal is to show that the social dynamics of coordination in these sort of local interactions, people just interacting one-on-one, can in some cases generate coordination. Now there's a really strong theoretical intuition, which is consistent with my earlier work, that says, look, if this person is interacting with this person repeatedly, that makes it more likely that they're going to coordinate than 2 people who are kind of selecting neighbors at random. Furthermore, if this person is interacting with this person and also they have a shared neighbor, it's going to make it more likely they're able to coordinate than people here who interact with repeated neighbors, but their neighbors are interacting with people they don't interact with. So you expect this to become the strong case for coordination, this to be slightly weaker and this to be the weakest. And that's what, starting with Ellison, 93, this literature really takes off in 93 with Ellison and Peyton Young, who really formalized a lot of this. And I'm just going to show you a quick simulation of that so the intuition will be clear. So this is a bunch of people laid out in a lattice network. This is a bunch of people laid out in a sort of random mixing. And what you're going to see is as people interact, links will show up. And if they coordinate with one another, they're just playing an A-B game, trying to coordinate. If they coordinate with one another, the nodes will turn red to show that they're coordinating. But of course, if they fail to coordinate, they'll turn gray again. So you'll see them kind of turn on and off as they try to coordinate. And the goal will be to see just if we play them next to each other in sort of real time, let's just say, equivalent comparison, what will be the dynamics and for the evolution of convention and coordination. So what you can see is the nodes are turning on and off, but you're getting these little neighborhoods of coordination, which is exactly what you would expect from that theoretical model. And those neighborhoods are spilling over to other neighborhoods, and eventually you get actually large-scale coordination throughout the lattice network. Meanwhile, on the same time frame, the random mixing case isn't producing coordination throughout the network. In fact, a couple nodes are occasionally coordinating, but then they're failing to coordinate subsequently, and it's sort of cycling around. Now, as anyone here who works in sort of complex systems or on the border of physics and computer science knows, in infinite time, noise can do pretty much anything. So if you run this infinitely, you can get coordination in these models. But what we're interested in is time scale. We're saying on reasonable or on comparable time scales, what do the dynamics of coordination look like? And here you get successful coordination in a network extremely quickly relative to this case. And this is consistent with the theoretical intuitions from all the work that we've had before on networks and social evolution. So the take home here is that local clustering reinforces coordination, and that increasing connectivity will slow global coordination. And where I want to push on this, and really what I'm going to talk about today, is this question of innovation. Now, that model I just showed you is used by a lot of people to talk about the diffusion of innovation, quote unquote. And that's because it's a term that sort of made its way into the literature through some of the work at Santa Fe and other places, Brian Arthur's work, and it's not wrong. I mean, we can say innovation is something that's introduced into a population. People are trying to coordinate, on Macs versus PCs or something. But innovation has a broader meaning that I think is relevant to us here, which is the capacity of individuals to spontaneously suggest options, the possibility that new alternatives are actually introduced into the population over the course of the dynamics. And so we want to sort of introduce this possibility for creativity into the dynamics, and we also we want to think about when that happens what this means from a network perspective. It means that instead of just having A and B in the population, C or D or double Z could show up somewhere else in the network. And I, trying to coordinate with my local neighbors, won't even have access to it. I won't even know it's a possibility until it makes its way over to me. And similarly, people in other parts of the network won't really know what we're doing until our options make it over to them. Right? So now you've got this sort of diffusion problem mixed in with this innovation problem, mixed in with this coordination problem. And I think this is much more like what happens in real life. When we think about the convergence of cultural norms and the emergence of new linguistic conventions, I really think that it's much more like this kind of social process where there's a lot of creativity going on, and all of these processes are going on simultaneously. And so to get a grip on this, moving from our formalized models into something more empirical, we need to be able to say, all right, what are the criteria we need to satisfy in order for us to really understand this process? And so this is this is the set of conditions we wanted to satisfy in being able to study this empirically. We want to say, all right, there's no a priori, there's no limit on the number of possible alternatives that are in circulation. Furthermore, it's not just that there's no limit at the outset, it's that there's no limit throughout the process. So even as the population is evolving, it's not that the number of possible behaviors needs to stay constant or go down. New behaviors can be introduced. So the number of possible behaviors circulating can actually increase over the course of the evolution. The expected payoffs are the same for all alternatives. This is really important because it basically means, look, I don't really have an initial bias for one behavior or another. Or if I do, it's going to be different from your bias. And so at the end of the day, all I really care about is coordinating. Because we don't really know what these behaviors are going to mean in any sort of predetermined sense. That is to say, unlike the Harsanyi-Selton situation where the payoffs are pre-assigned to the options. Individuals attempt to coordinate locally. So this is really, these two are tied together. What this means is I don't have a view to the global population. Not just, I mean, first of all, informationally, I have no idea what's going on. But more importantly, in terms of my incentives. It's not as if I'm rewarded for coordinating what the rest of the world is doing. I'm rewarded for coordinating what the people I interact with are doing. And this is really important. If you think about the people in your neighborhood, the people at your job, the people you interact with socially in your family, right? It doesn't really matter what the rest of the world is doing. When you're interacting with them, you need to be able to coordinate with them, right? These are the standards that guide our everyday lives. And if there's an informational source that we're all paying attention to, well, this can coordinate our behavior. But if there isn't one, then our behaviors really are coordinated just based on these local interactions. So the way that we formalize this is in terms of a naming game. This is a kind of a really simple model that captures the essential principle. And it's actually based on a really nice game by Wittgenstein, where he invented what's called the slab language, where two agents are both looking at an object. And they have to point at it and call it the same thing in order to be able to do anything. So it's kind of a functional requirement of work that we have to be able to coordinate on talking about the same object. And really, it's just a trial and error process. Two actors are kind of pointing, they're both suggesting options, and eventually they both coordinate on using the same word for the same object, and then they can sort of go about their business and get work done. Now, empirically, it turns out that the obvious way to study this is to put two people in a lab and have them do this. It turns out to be way more complicated than you'd think. There's a lot of work, particularly from the late 80s and early 90s that spent a lot of time doing this. But interestingly, the people who started doing this have actually gotten frustrated working with humans that have moved to doing this kind of work. where this is actually from Sony Labs. The main guy who was working on this, Luke Steele, now works for Sony and works on these robots. And this is essentially like the literal Wittgensteinian naming game, where the robots are pointing at these objects and trying to sort of coordinate on them. The interesting thing about this is like, okay, let's say in the abstract that you solve this problem with 2 robots. What does this tell us about the large-scale dynamics of coordination when you've got hundreds or thousands or hundreds of thousands of people connected in networks? It doesn't really tell us much, right? Because the whole problem that we're after is this problem of aggregation and how the network connectivity affects this. So this is where all the empirical work I'm going to talk about kicks in. And so it's useful to say that a lot of work, right, has been done in this area, and a lot of really, really good thinking. And the reason I'm going to present this method, which is sort of a new way of approaching this problem, is because this work can't actually answer the specific question that we're after here. A lot of really good work has been done in laboratory settings. And they started, again, with 2 people interacting with one another. And some of the work has actually built up to 4 people, and networks as large as 10 people. So a lot of people now, and this is sort of a footnote, but a lot of people are running experiments on the web, collecting data, and so forth. I think it's incredibly important to have a model before you try to do that. And the reason is because you're collecting data in an unknown parameter space, and a very large parameter space. And so without a model to kind of guide your intuitions, it's very hard to know what those data actually mean or how robust they are in different directions. And this is a great example of that. So when our model of the naming game dynamics showed that below a certain population size, a critical point actually, there's a critical transition, and it's about 20. Below a size of 20, you get dynamics that look one way. And if you looked at populations that are above 20, you get dynamics that look a different way. And the results you get are essentially the opposite. And what that means is that all the small group laboratory results, while interesting, don't tell us about what the dynamics look in larger populations according to these models. And this can seem like bad news. It means we have to collect large data. But it's not bad news. It's really good news. Because what the model means is that if you collect data that are above that critical point, those results generalize all the way up. Right? So you actually don't need 61 million people in a data set to make an argument about 61 million people. You need a data set that's larger than the critical point that can reasonably be generalized to a large population, and then those arguments generalize up. Right? And so that's what we're going to do. We're going to start basically doing experiments that are above that critical size and then show that they generalize up to larger populations. All right, so there are some experiments that have tried to do larger groups, like 30 people, 36 people in networks. But the way that they've been done, and this is, again, because these used real-time linguistic coordination where behaviors actually evolved, these experiments in larger groups were classic economics experiments where people were given options A or B with fixed payoffs and also incentives for global coordination. Right? So when you give people all of those institutional constructions, then yes, they can coordinate. But the whole question we're after is, well, what if we remove those institutional assumptions? Can we get coordination off the ground when it's live and spontaneous and all the behaviors are endogenous? And so that difficulty of collecting large-scale, real-time endogenous interactions also without any sort of economic limitations on the behaviors has been hard to do. One of the answers people come up with then is they say, well, go to big data, right? Because that's what big data are. They're really large-scale data of real-time interactions. Once we do that, then we lose a grip on all of the scientific controls we need to rule out the other explanations. There's some kind of pre-existing institution, there's some kind of exogenous influence or social control through authority. And then finally, the point that I was mentioning earlier is even if you could satisfy all of these in your one perfect pristine data set, you would only have really in your one data set a single observation of a single population. And what we want to be able to do is show that we can reproduce these dynamics over populations again and again in a systematic way. So this is what motivates the method. And the method here is the social petri dish, the sociological experiment, but the basic intuition is I can create a world A and a world B, and the differences between those worlds are invisible. Right? The people in that world don't know that they're in world A or world B. Nevertheless, endogenously, world A will just grow some sort of collective behavior, and world B will fail to grow. And now, if you have this, and it's as systematic as you believe, you should just be able to reproduce petri dishes again and again and again and again and get the same result. And now you have statistics over populations instead of over individuals. And that's the sort of goal we're going to do today. So the experimental study is structured just like the name game. So people show up to the website, they're recruited. I can talk about this more of people who are running experiments and thinking about these sort of logistical questions. They're recruited en masse from basically advertisements that are sent out on the web where we say people come play online social games, people come to play the games, and then when they sign up, they're basically put into a waiting page and they're slotted into pre-existing network structures. When the game starts, they're given an object, in this case it's a face, that they're told that they have to name. Each person tries to say a name and tries to coordinate with their neighbor. And over a series of interactions, we try to see whether or not people coordinate with the people they're interacting with, and also whether the community coordinates as a population as a whole. And our goal then is to see whether social norms emerge over large populations. So this is what it looks like. We recruit subjects, they come to the site, and you can imagine now what's happening, right? So people are getting this invitation and they're pouring in. But in order to run an experiment, we've got people interacting in real time, especially in large networks. You need bursty recruitment, right? So 1,000 people over 2 months is useless to me, right? I need 100 people in a day, right? You just need people to show up right then, and not just in a day, but in the same 5-minute window. So they all come and they're all playing. And so what this is essentially a page that, as those people arrive, has to keep them entertained and kind of explain to them what's going to happen next, while we're waiting for enough people to show up that we can fill a network. And once enough people show up to fill a network, then we slot everyone in simultaneously, and the game starts. So the game page looks like this. And if people have questions about this, you guys have kind of just let me roll for a while, which is nice. But if you have questions about this page, ask them, because when I present the results, they might not make sense unless you understand the actual user experience. So basically, the game starts. People see on the left-hand side a list of other players. They see the avatars and usernames, and I'll say more about this. Then they see an image, a face in this case, and a text entry box, and they have to type in a name for that face. Now they don't know, one of their sort of the partners is among this list, but they don't know who that partner is, which is to say we haven't signaled to them which person they're playing with. That's really important for the experimental design. It tells you your time limit, which means that you can't just sit there for an hour and a half, right? This is a real-time game, so you have to sort of move through it fairly quickly. And it tells you where you are. So you know there's going to be 20 rounds in this game. You're in round 1. If you match in that round, then it says match on round 1, and it advances you to round 2. So you kind of know where you are at all stages. And of course, it keeps a real-time tracker of your winnings. You're rewarded for cooperating. So if you and the person you're interacting with say the same name, the machine comes up and says, you matched. You said the same name, and you get the reward. In this case, it's completely nominal reward. It's like 25 cents or something. And if you fail, interestingly, then the machine comes up and it says, you failed to match on this particular round. You said this name and your partner said this name. So now you're learning. You're seeing what options are in the population. You see that your partner said a name that you didn't say. And you're kind of accruing this memory of what names are in circulation. Again, however, you don't know who your partner was. Furthermore, this list of 12 is shown to everyone in every experimental condition, which means that you can't tell what the topology is, nor can you tell what the population size is, because there could be 20, 30, 40, 50 people in the network, but all you see is this, right? And that's really important because it keeps people blind to what the state of the world is around them. All they really care about is this local interaction process. One further thing is that the design of this, I tend to think about these as analogs to real experiences we have every day. I think of this as kind of a carnival game. One of the things we like about carnival games is that they're difficult. Right? If it were too easy to get the ring on the frog, you just wouldn't care about it. Right? But you know it's rigged. There's a trick there, and part of the fun of it is to try to figure out what that trick is. And in some sense, this was designed in that way. So when people match, they win money. But when they fail to match, they lose money. Right? So actually we decrement them as well, which keeps them engaged, keeps them sort of paying attention, because they fall off, they can start to lose the winnings they've earned. If they go below 0, we can't take their money because that's called gambling, and Massachusetts and Pennsylvania both frown on that. So yeah, we don't do that. But the basic dynamics are here. Are there any questions before I move on to the results about the user experience? In the basic, yep. Yep. Sorry. So you only see at each, so that's important, at each interaction, you're basically playing with one person, and that's it. That's all you know. And so you put in your answer, you hit enter, and then it's reported back to you what you said and what that person said. And that's your information about the world. It's just that one interaction. And then you kind of advance to the next round, you're matched again, and you play again. So there is no kind of other group or group size or even group concept as part of your playing experience. Okay? What's that? If there is, well, that's what we're going to. I'll show you the results then. Yeah, we should look at the results. But is there any question about the experience? Or yeah.
Did they know something about characteristics of the population of the other players? Like, are they all Americans? Are they all
Right.
English speakers? Because that will certainly affect my choice.
Right. Yeah. So no, they don't. Is a great question. And also, what we'll see in the results is the names that come up are really varied in the sort of ethnicity that they try, and also people try interesting things. They also try to cheat, which is really, so I ran this when I was first at MIT when I was running this, and some people would paste in code, right? You got to expect this to happen. So people would paste in code to try to hack the system, and so like this is unbounded. You can actually put in an unbounded number of characters here. So it was like 150 lines of code which show up. I'll show you in the dynamics, but they actually show up in like the list of possible names. No one matched on that.
Along the same lines, did you recruit, like at MIT, did you recruit from students, or did you try to recruit from all over?
I recruited all over the world. The recruitment question is, of course, of interest scientifically, but also for anyone who's doing this like realistically and logistically. We used, it's called Adweek. It's amazing. The stuff people do online is like all of the experiments I run, I'm always amazed that people actually care. I mean, that's the thing is that people do all these behaviors online. The previous stuff I did was on the spread of health behaviors, and I built like an online health community, which is something I personally would never do. But like thousands of people came up to sign up and join the health community, and they cared. They were interested. They participated for months in it. It was amazing to me. And this is similar. Like people subscribe to this Adweek, which is basically spam. And they get it in their email box, and it's advertisements about stuff to go do, or products to buy, or I guess in this case studies to join, and they actually click on the links and come sign up and do this, right? So there are these ways of sort of getting people who are interested in doing stuff to come do stuff. Yeah. Yep.
So what's the experimental condition and the control condition in this game?
Yeah. So okay, then we should get to the results. Basically, those three networks that I showed you, the lattice network, the random network, and the fully mixing network, are the kind of three base cases. And one thing I didn't say about that slide that would be useful is that you'll recall, I can go back to it, but do you recall that left-hand side was the lattice, the middle was the random, and the right-hand side was fully mixing? That continuum is actually a theoretically exhaustive continuum. What that means is, if you say to me, but what about small world networks, right? Actually, the dynamics of a small world network occur between the lattice and the random network, which means if you understand the lattice and the random network, there's nothing nonlinear that happens in there. It's a smooth transition. And so those two endpoints actually encompass that entire space. Furthermore, if you say, well, what happens in a scale-free network, a network where there's hubs or some kind of degree distribution, the dynamics of a scale-free network or degree distributions occur between the random network and the fully mixing network. And again, it's smooth. There's no nonlinearities in there. So by just tracing these endpoints, we've actually got the sort of encapsulated dynamics of the sort of the interesting space of networks that we talk about. Yep.
So you're not really opposing like an either-or condition. You're sort of allowing them to experience it. There could be a continuous variation of experiences.
Well, in this case, it is either-or because I run basically three conditions: the lattice condition, the random condition, and the fully mixing. And
the real world,
there's lots of in between. But the beauty of the model is we know, well, based on these dynamics, where the real world will fall, based on the structure of the network. Yep.
Just to be clear, how are those three conditions operationalized? Like, I'm not getting from this slide how you make someone geographically close or far.
So it's very much like the model I just showed of the other dynamics, where people are, let's advance to this, people are basically slotted into positions. So there's a network structure, they're slotted into these positions, and the game hasn't started yet. They're just kind of sitting there. And so there's like a 2-second delay for this process to take place. Now, meanwhile, we've randomized people. So there's, meanwhile, sitting over here, there's a random network, and sitting over here, there's a fully connected group. And so we're just randomizing across, and then when all three fill up, we just start them. Yeah. Are there any other questions about, I'm going to get into the results. The results are super interesting, so you want to see them. Go ahead.
You
So that's an interesting question. That's kind of an end of talk question, though. So, but no other questions about the dynamics here? Yeah, OK. So what I'm going to show you is, and this is one of the beautiful things about collecting these data, is that I'm not going to show you, I mean, I will show you statistics later, but I'm just going to play for you the real-time data. So, no analysis, just the actual behavior. What happens here is that as people choose names, the nodes change color, and the nodes are, corresponding to the names. And I think the easiest way to do it is it's going to play here on the right-hand side is basically a histogram. So you're going to see as people enter in names are just going to pop up. And the number of people that are using that name, the color bar associated with it is going to get bigger or smaller, right? So you can see the histogram grow and shrink as names become more or less popular. And as people interact, the links will fill in, just like in the other simulation. The thing to note is that if people coordinate, the link between them will be the same color as their coordination. If they interact and fail to coordinate, the link between them will just show up as white. So you can see them interacting and failing as well. OK, so you can see the name list starting to fill in on the right. And you've got people choosing names all over the network. You see some people starting to coordinate. And very quickly, you see groups start to form. You see this group up here, which is Sarah, this group down here, which is Elena. And I'm just going to pause it for a second so you can see some of the things that are happening. So people type in gorgeous, sunshine, blue eyes, right? I think of these as like cute attempts to cheat. Right? They're like, I'm not going to type in a name. I'm going to type in a category. Some people typed in things like copy me, Simone. Right? And we're not supposed to type that, right? But like you're supposed to get that that person's saying copy me. So these were all attempts to kind of get outside, right, the structure of the game. So none of those attempts worked. But none of those attempts to sort of outsmart the dynamics affected the dynamics at all. And there are interesting things to see here about a name sort of percolating up, and now there's sort of some confusion about the people they're interacting with. Now this name sort of spreads down here, now that person. Right, and so the dynamics here are far from a diffusion process where it just goes in one direction. They actually, names circle back, they become more popular, less popular, and you get this kind of entrenchment here locally, right, around a norm. And then you had one here, Elena was growing, but then you had some confusion on the periphery. Basically, these border areas form. And that confusion on the periphery can either die out, or it can actually start to percolate through like the cultural cluster and actually start to disrupt that cluster. And the other thing that happens here that you wouldn't see in a model but is very, very human once you see it, is that people in those border regions, they're trying to just, they're going back and forth. They see A, they see B, now they see A, now they see B. And they're trying to coordinate, but sometimes they just get frustrated and say F, and that's it. And they go off. And oftentimes that's, or some other letter. And oftentimes that's ineffective. But sometimes that new suggestion actually does wind up percolating through the rest of the network. OK, so what we see here, however, overall, is that these dynamics are ineffective at generating sort of large-scale coordination. We get these groups forming. These groups are essentially competing groups. And because of the boundary formation on the edges, we don't get coordination of the population. So we say, well, maybe by putting people into a random network, this will solve the problem. The dynamics start off, and the sort of images are the same. We see people choosing. The people they're linked to are lighting up. And we see a few options kind of popping up as early winners. But we also see these options kind of, again, forming reasonably sized clusters. This kind, Lisa, Jane, Jennifer, Julia are sort of the, Sarah's now in the mix again, are names that sort of pop up and wind up forming these groups. And even though these groups aren't geographic in the classical sense, they're not like locally reinforced in a geographic sense, they do wind up kind of becoming cemented among a small group of people who sort of interact regularly with each other, and then dissipating as you get farther away from that local group. One thing to note here is that the number of names suggested here is larger than the population in every case, right? Which means it's not just the case that this is 24 nodes. It's not just the case that you get it's not just the case you get 24 people suggesting a name on the first round, and then the active population winnows. In fact, what happens is there's frustration, there's spontaneous creation, there's responsiveness, there's also like a lot of wordplay. People will put in a name and then change one letter, S-A-R-A, S-A-R-A-H, right? People play around with that. abbreviations, and manipulations to try to figure out where the best coordination spot is. And then, all right, so I'm going to play for you now the final. Was there a question here on the results, or can I go on?
I'm just curious how the names that show up correspond to like how popular the names are.
Yeah, so
Overall population.
right, and you'll see that in this one as well. The interesting thing is that the names that show up in that list were varied. And what we found across experiments was there was no one name that systematically came out on top. We ran this both across genders. We had large variation in the faces we used, gender and race. And the names that circulated were basically there was no statistical difference in the name list across these, except the gender names were different. But in general, across the list, we found a wide variety of options. And more importantly, the selection of a winner wasn't determined by the set of options available in the population, which is to say that options that would win in certain cases would not win in others. Yep.
If you map those names back to the people, do you have a scale-free network with that then too?
Map those names back to the people. No.
Those names have a cluster of people who are suggesting them.
I see. So you're saying the popularity of the names. No, it doesn't create a network in that sense. That's a good question. I'll talk about the statistical analysis of the names at the end. Yeah, but it doesn't do that. But let me present to you the final results, which is letting people sort of mix at random. So now it's the case that everyone is picking a stranger to interact with, and at the next round they pick a new stranger. You can see the name list grows very, very quickly. It grows faster than it did in the other two cases. Because essentially each interaction is a new interaction. You don't have any kind of familiarity. There's no kind of built-up history with these people. So the name list explodes, even though the set of names is growing much, much faster in this case. So the sort of ecology is a much bigger ecology. You're actually getting one name starting to take off and become a dominant player. And then you can see once this happens that the explosion is fairly quick. And then that sort of percolates really, really strongly throughout the network and winds up generating sort of convergence throughout the population. And so it's a really interesting thing. It's one of those results where without realizing that there's so much theory on the other side, you can say, oh, right. The epiphany happens, and then you say, yeah, this makes sense. But the striking thing about it is just how systematic these dynamics are. If we compare in the experimental results the spatial network and the random network, this is basically the set of options bouncing around. So the reason it's so messy down here is because these are all the names, and the y-axis is the relative popularity of those names. So 1 on this axis means that name has 100% of the population, and 0 means that name has 0% of the population. And so you get names that have, in this case, about 40%. That's a big chunk of the population. But then interestingly, they start dying back down. And you see this in the random network too. You have names that jump up to almost about 40%, and then they die back down. Right? So you get these sort of spikes in popularity, but they don't wind up generating this sort of global convergence, the emergence of a convention. The interesting thing here, I think one of the most compelling points about these data is that you see this name here that winds up taking off. It basically reaches 30% of the population, and then nothing ever competes with it again. It explodes. So there's this very large literature on critical mass dynamics. And the question almost always is, what's the size of the critical mass? What do we need in order to get that kind of takeoff effect? Well, if you saw this, you would say, well, it needs to obviously be significantly larger than 40%. 40% is not enough, right? Whereas if you saw this, you would say, 30%, that's the key number. We need to get 1/3, and then we're golden, right? So it's really, the critical mass question isn't properly formed. It's really not a matter of just what the size of the critical mass is. The structure of the population determines whether or not you can even get these dynamics off the ground in the first place. The next thing, and this was for us the kind of aha moment, is to look at these dynamics compared to the theoretical model. And the thing is, if I covered up theory and experiment, these two would be indistinguishable. Not just in terms of the general dynamics, but even in terms of the size and scale of the fluctuations before takeoff. And so what this tells us is that the theoretical model with these extremely simple agents just trying to coordinate with one another does a very, very good job of approximating these human dynamics of people in real-time endogenous space just coming up with options and trying to coordinate with one another. For the physics people in the audience, it's useful to just get a sense of what's actually going on when takeoff happens. This is basically what's called symmetry breaking. So at this stage, before this happens, all these options are essentially equivalent. Any option can win, right? Some get big, they go to 40, they die down, they go 30, they die down. And if you look at the distribution of options in the population, it's basically a Zipf law. It's like, it's anything can happen. Even the small options can become more popular. What starts to happen at this transition point is that distribution becomes increasingly skewed. So one option is getting more and more of the share, and other options are starting to die out. So now we have real extinction happening, right? The set of population options in the population is starting to dwindle. And then up here, you've got this really skewed distribution where basically these options are off the table. And now you've got one dominant option and maybe a competitor. But at this point, this is different from the voter model and different from models where there can be sort of constant switching. Because at this point, it's a fait accompli. That option's going to go to fixation. There's nothing you can do about it. It's basically, it's a big winner. Now, for our purposes, when we first got these results and ran them with populations of size 24, it's a weird thing when this happens. When you have a model, you run an experiment, and you get like the result. Because your initial reaction is, yay, and your second reaction is, oh God, should we even run it again, right? Because it was perfect, and it's never going to be perfect twice, right? And so that was actually, it was kind of that conversation where it's good to have a co-author. We kind of looked at each other and said, yeah, so, and that social pressure was good. We forced each other to run more experiments. And so we ran another one of these at 24, and another one at 24, and we're getting the same, like literally the same results each time, which is satisfying. But then it started to raise that question of, we argue that this generalizes. We're above this critical point. This generalizes to infinity. Do we believe that? This is a complex social process. Does it really just generalize as simply as we think? So the next question was to see if we could run it with a larger population. So we doubled the population size. Also, imagine this logistically. So now we're going from, we've had to solve this problem of getting all 24 times 3 people in the experiment simultaneously, so we could like randomize them. And now we want to say, let's increase the population size to 50 for 48 people. And do this again, both the recruitment, which was harder now, and also the experiment where the results weren't expected to be as good. But we got like literally the same exact results. And interestingly, like on the same time scale too. So we doubled the size and the time scale remained the same. And this is what the model predicted, but again, it was surprisingly exciting. And then it was, at this point, it just kind of became fun. We were like, all right, let's cross our fingers and double it again. And you kind of say that thing of like, well, if we don't get it, we just, I don't know. These are good results, right? So we ran it again and then got the results. This was, you can see 30 rounds, 30 rounds. So this is played out to 40 rounds. And we got these results. So this is 100 people. It's 100 strangers online simultaneously interacting, just shooting names at each other, right? And within a couple minutes, and this time scale of coordination is actually faster than what's predicted by the model, right? Within a couple minutes, they're all just coordinating on the same name that they just created out of scratch. And then when you look at these replications over all of the replications, so this is the spatial and the random network iterated, and this is the homogeneous network iterated, you get results that are, you can do a statistical test on this, and the result is significant. But I think that the qualitative effect is actually more striking, is that you just look at it, and it's really clear that there's a significant structural effect of putting people in different networks on generating radically different collective outcomes, right? And this is, to invoke what I said at the outset. This is kind of this, this Durkheimian, Sirmelian idea that we can just structure populations differently and produce these social outcomes in a systematic way. So just to give you a sense, and I know I'm at the end of the time, to give you a sense of where this is going. Does everyone remember this? Is everyone sick of this? Yeah, okay. So one of the advantages of being in the Bay Area is that every party you go to, people are talking about stuff like this. And someone just pointed out that this was relevant to the kind of problem I was thinking about. It hadn't even occurred to me. And so I Skyped with my grad students and said, why don't we just put that up? Why don't we run the name game and we'll put that up? But this time we'll see if we can actually generate the norm, because it's really flexible. People choose A or B, and there's always neurological and psychological explanations. There's some level at which if you get massive coordination on a behavior and it's a flexible behavior, there's got to be some sociological component to it. So we should be able to put people into a network, have them play the game about what color this dress is, and see whether or not we get coordination on one option. And then we should be able to kind of mobilize the other opinion and see if we can get the population to switch, see if we can actually generate flexibility from a minority norm that would wind up kind of changing the social order. These are the dynamics. So you see this playing out over time. People coordinate very quickly on black and blue, which is the wrong answer, by the way. And then we've got this, some people saying here, and then it goes to 0. And then we put in a committed minority, a group of people who are, these are my grad students in the network, who are advancing this option. And now you see it go up, and it starts to go to 50%, and then ultimately switches. And now you have white and gold as the dominant option in the population. And this is the stuff that we're working on now, is this question of how effective, once we know how these dynamics work, right, we have a very good grip on how coordination and large-scale consensus can emerge in these populations, then how effective are we as a small group in controlling these dynamics? One of the questions that came up, it hasn't come up yet today, but it might. One of the questions that came up was, someone in the audience once said, well, if you put a face like this up, right, you could never get a name, right, that was like an African-American woman's name. It wouldn't happen. It's impossible. So your experiments are limited. And to me, like, the light bulb went off. I was like, well, that's exactly the point of what I'm doing, is to argue the opposite. Right, is to say that these dynamics are completely flexible, they're endogenous, and those norms aren't as stable as you think they are, although they feel very concrete to you. So we ran this experiment where we had people, these are 4 names that are bouncing around, and then we had one name win, and we sort of kind of put some options in the population artificially to see whether or not they could take off. And what wound up happening was the population actually wound up converging on Nia, right, as the name for that guy. And it's the kind of thing that a priori you'd be like, that's not possible, especially if names like Hans are in circulation, And so the point here is that the dynamics here are governing this process of global coordination, not the particular options in circulation. And there's a lot of really interesting implications about this, I think. I'm really interested in this idea of the emergence of gender conventions. There's this really fantastic work done by Cecilia Ridgway since the early 90s, thinking about gender norms as these endogenous social conventions. And she's sort of moved it into this sort of very applied gender literature. But where it comes from is this really interesting kind of theoretical application of Blau, thinking about what it really means to talk about a social convention and even a status characteristic as something that's created as people interact with one another. And I'm working on experiments now that actually try to see if we can generate that process in real time. Of course, everyone's always interested in health applications. And of course, these results are general to social norms and conventions, right? So I'm talking about linguistic coordination, but of course, we talk about coordination in diet and exercise. And again, when we model these things, and I'm guilty of this too, we model these things, we talk about them as binary things. Did you improved exercise or not, right? What does that mean? It's a mathematical convenience, right? How much do I exercise? How many days a week do I exercise? This is a completely flexible, continuous parameter. And I'm adjusting this with other people. I'm responding to what they're doing. They're responding to me. And we're figuring out a norm. And so this is the kind of thing I think of as kind of the next step for thinking about the applications of this to health as well. One of the other really interesting directions to go in with this is thinking about collective intelligence, right? So what I showed so far is how people can coordinate arbitrary norms. But what if the norms actually were right or wrong? Right? What if there was some objective standard by which to evaluate these answers? How does this connectedness affect the kinds of answers we get? And in some senses, right, Lazar and Friedman really argues like, well, maybe it's not good to have this kind of global coordination because people coordinate too quickly on something that's suboptimal, right? And so we're kind of exploring how these dynamics interact with the kinds of answers people get. And this actually matters because it interacts with these kinds of problems. People interact online in these online health spaces, and this is, again, something I wouldn't have known before running those previous experiments. But people exchange their health information. They post their recent medical charts. They talk about the medications they're taking, and they advise each other. It's amazing. People say things like, you shouldn't be taking that medication. You should take this one. Don't go to the doctor. Go to this one. Join this randomized controlled trial and try this drug. And people do it, right? And so it's really useful to know what kinds of coordination is going on in these networks and what kinds of medical decision making, whether it's good or bad, is actually coming out of it. And finally, from the position of the last thing I was talking about with the committed minorities, the groups trying to mobilize social change, when is a vanguard most effective? And I feel like I really want to, it's like brings out the sociologist in me. I feel like I want to say a small group of committed people can accomplish anything. This idea of the political vanguard overthrowing a dominant view is something that's obviously going to be. I mean, we want to get this out before the upcoming political, frenzy, right? So, I mean, there's a lot of interest in that question, and it's something, obviously, that we'd like to pursue. So the big area here that we're interested in is social change, social coordination, and the question that motivated us from the outset was, can these social conventions emerge endogenously without any institutions really governing that process? And we found that yes, in fact they can. So this just came out with myself and Andrea Barron-Kelly in PNAS like a month ago. And interestingly, despite all of these implications about social change and social order and political mobilization, I think are so interesting. The press on this was about baby names, right? That's the press coverage on this paper. Was, why do people coordinate on baby names? And it's amazing. Everyone thought that was really interesting. And I guess it is interesting, but I was like, what about social change? But that's fine. And so, yeah, we really want to know about how these dynamics of small groups can generalize up to initiate large-scale social change. All right, thanks very much.